Hi, my name is Tom Badgewell. I've spent my entire career in the world of process control. That includes control consulting, academic research, product development, and frontline support in a refinery. And I got to tell you, open process automation is the most exciting thing that I've seen since the emergence of model predictive control in the early 1980s. Now, the COPA QuickStart is a collaboration between COPA members and the engineering teams. And I'm very pleased to be the first one to show it to you. All right, the first thing I need to tell you is that the COPA QuickStart system follows the OPAS architecture developed by the Open Process Automation Forum. We'll start down at the bottom with some distributed control node I/O modules from Stahl and from Phoenix Contact. Now, the most important thing to talk about here is the fact that we've separated I/O from compute. You don't have to have compute and I/O modules from the same vendor. That's really important when you're ready to upgrade your compute capability because you won't have to lift field wiring or replace any of the I/O. Now, the DCN I/O is taking in, sending and receiving 4 to 20 milliamp signals from our simulator down at the bottom, and it's converting those signals to standard OPC UA format. That allows the signals to be used throughout the COPA QuickStart system, and it gives you unrestricted access. At the next level, we have a power supply from Phoenix Contact, and we have an industrial Ethernet switch from Cisco. And then we get to the distributed control node compute section. Here we have modules from ASRock and from VCal. And on the ASRock, we'll be running our conventional control system that I'll demonstrate in just a moment on the fired heater. So there we have a Codesys 61131 standard runtime running on the ASRock. Now the VCals down here, you may see that 3 of them are not turned on yet. We're going to be adding those using some orchestration capability in a later demo. All right, so let me get to the top, and that's the advanced control platform. And here we have 2 data center class computers from Supermicro. Now, these host a lot of the management software, HMI, Historian, Systems Management, orchestration, other applications, everything that you need to operate, monitor, and manage the entire system. Now, the ACP is a powerful and flexible platform for advanced control strategies, for monitoring, and for AI applications as well. And the fact that it has high availability and low latency means it's a powerful foundation for digital transformation applications. Okay, so now we'll talk about a fired heater control problem that we've set up so that we can demonstrate the features of our COPA QuickStart system. And to do that, first I'm going to take you to this HMI that comes from Inductive Automation's Ignition product. And here we've shown a fired heater. It's being simulated in the COPA QuickStart system. And this is a particular type of fired heater. It's a simplified version of one that you would see at the front end of a petroleum refinery. And its job is to vaporize the oil that's coming in so that it can be separated and processed in the refinery. So starting at the front end, the oil comes in and gets separated into 2 separate streams that we call passes. The 2 passes go through the heater where they're warmed up by flames from a fuel gas system. They're recombined and then go out to the rest of the refinery. So along the way on each pass, we can control the flow with a flow controller. We measure the flow here. We measure the inlet temperature. We have a sensor here that measures the outside of the tube because we want to make sure we don't melt the tube. And then we have a sensor here that measures the oil temperature coming out of the pass. These things come together and we measure the combined temperature and flow coming out. Now, to operate this heater, we have 3 flow controllers that we can use. I mentioned that we have a pass flow controller here on each pass. Then we also have a flow controller for the fuel gas going in at the bottom. Okay, so how do we operate this heater? Well, there are really 3 things that are really important. Okay, number 1 is we'd like to make sure that we reach a certain temperature. We want to make sure we vaporize all the oil. Secondly, we'd like to send as much flow into the heater as we can. We'd like to maximize the flow rate because this is at the front of the refinery, and this flow rate, the profit of the refinery is directly proportional to this flow rate. And then third, for safety reasons, we want to make sure that we don't burn up these tube skins. So that's essentially the problem. We want to maximize flow rate. We want to keep this temperature. But most importantly, we want to make sure we don't burn up the tubes. Okay. So we're going to talk about two control strategies in this demo for this problem. The first one we'll talk about is more of a conventional control strategy using PID blocks, sum blocks, select blocks, things that you would find in any standard DCS system today. And we're going to build that strategy with a product called Codesys. And the individual control blocks that we're using, the PIDs, low selects, and so on, come to us. They're implemented by a company called Nova Smar. Now, they're implemented in a standard IEC 61131 manner, okay? So I'm showing you these two strategies. I don't expect you to read this. The print is way too small. I just wanted to show you that we have a number of blocks connected together. PIDs are here. We have some analog input, analog output blocks. And this strategy at the bottom is designed to control the temperature of the heater. This strategy up here is designed to control the total flow rate. So they're implemented in this Codesys IDE, then they're downloaded, and they're downloaded to one of these ASRock modules. All right. And the downloading, the automated installation of these is something that's taken care of by Seaplane AI's Fusion Management software. Okay, so let's come up to the top again to this HMI, and let's take this control strategy for a little test drive. And the way we'll do that is we're going to increase the set point of this outlet temperature controller. We'll go from 750 to 790. And so you can see the control, the PID control here is calling for an increase in fuel gas so that we can warm up the heater and get the oil to the correct temperature. Now, as that's happening, the tube skins are also going to be warming up. And so part of this control strategy is that we have some controllers here that are looking at the difference between the tube skin and the tube skin limit. And they're also calling for their own values of the fuel gas set point. And when this controller, that's controlling the outlet temperature, calls for more fuel gas than this controller that's looking at the tube skin, then this one gets selected and it overrides what the outlet temperature is calling for. So this is called an override control strategy. And this is an example of a very conventional control strategy that you can build using PID controllers, select blocks, and so on in just about any distributed control system. All right, so we're watching it come on up. And let me just say that this may not seem that remarkable to you because you can do this on just about any DCS. However, here we've implemented this control system in a very decentralized way. We've done it using standard 61131 control blocks. We've done it with the control logic separated from the I/O, and we've done it with software and hardware from a variety of different vendors. So it's really quite remarkable what we're seeing right here. Now, you may have noticed that we're above our limits now on the tube skin temperatures. And very shortly now, we'll be selecting the override. And once that happens, this control strategy, it prevents the tube skins from burning up too much, although it is violating a little bit the limit. However, it's not going to do anything really about that situation. It's going to sort of park the heater in that mode so that the best you can do with this strategy is keep the tube skins from getting too hot, but you're never going to reach your desired set point on the outlet temperature because this strategy isn't smart enough to prioritize and take advantage of other degrees of freedom that it has. All right, and now let me introduce Brandon Williams, co-founder at Seaplane.ai.
Thank you, Tom. Seaplane AI is a California-based software company that has been working in the open process automation forum for the last 4 years to address the challenges of systems management. Although I've spent much of the last 15 years of my career in enterprise, telecom, and cloud software, my connection to industrial systems goes back to managing nuclear power plants as part of the American submarine service. Let me show you just a couple of the QuickStart systems management features. So I'm going to bring up another UI screen written in Python that is getting real-time OPC data. With the control data liberated from proprietary data formats and subscription access, it gives a lot of freedom of how and where your data can be used. This screen shows our fired heater simulation. The PID controls are running in the ASRock Industrial Distributed Control Node here, labeled DCN3. And the first thing I'm going to do is increase the set point to 780 degrees. Just to show that it's operating normally. And so, as you'd expect, you can see on the left that there's an increase in the fuel gas flow, causing a rise in the temperature. And if there's a fault or connectivity issue related to the primary application's DCN compute node, as I said, DCN3, the control functionality will be automatically shifted to a redundant application that's running on another DCN compute node, in this case, the VCAL. We've created redundancy for this control application using software, not through one-to-one hardware redundancy. Just as a note, a secondary control application could be running almost anywhere in the QuickStart system, including up in the ACP. So we're at a new steady state. I'm going to change the set point again from 780 degrees back down to 750. And as I do this, just to add a little bit of drama, we're going to simulate a fault or a failure. So I'm just going to disconnect the network connection from DCN3. And as you would expect to see in a resilient, highly available architecture, nothing happens. And in reality, we actually had to slow down the software handoff between these systems so that you could actually observe that there had been a signal interruption. But there was no discernible loss of continuity in the data being provided by the I/O. There was no loss of view of the state of the process, no loss of control, since the backup instance of the control application was able to take over faster than the temperature could move. This modern technique of high availability using software and virtualization can provide fault tolerance to most use cases. And it's proven to be equally reliable and vastly less expensive than redundant hardware. Another significant feature of an OPAS-based architecture is the ability to evolve and upgrade the control system even after plant commissioning. Let me demonstrate this for you now by adding and discovering new devices to incorporate them into your control strategy. As Tom mentioned earlier, being able to upgrade the compute capabilities without touching the I/O is a significant benefit. Using the Seaplane AI Fusion system, we're going to take a look at the rich information about the control system infrastructure that's ingested into the Systems Management Information Model using DMTF Redfish. DMTF Redfish is an important foundation for intelligent management and interoperability of open systems. It allows machines to describe themselves to other systems, as well as to allow human users to have detailed insight into individual machines. Let's look at the COPA members' implementation of Redfish from the perspective of Seaplane AI's system management platform. Okay, so I'll start by showing you the system management view of QuickStart. You can see our DCN compute nodes here, 5 from ASRock and 1 from VCAL. And you can also see 2 of the DCN IO nodes here from Phoenix Contact. But now we want to add some additional DCNs, as we talked about earlier. Why might you want to do this? You may want to expand the scope of your control system, or you may have a specific use case that requires best-of-breed hardware. So I'm going to add 3 DCN compute nodes here, turn them on, and connect them to the network. Okay, so while these come up, these are Intel i7 industrial PCs, and they're coming online. So again, we'll just take a filter view here, look at all the VCAL devices, and we have 1. So with the new devices are starting up, let me show you the rich information collected by Seaplane's system management application. Fusion builds and maintains a sophisticated information model of the control system. Let's clear, filter, and we'll look at one of these ASRock industrial devices. There's lots and lots of information that we provide here. This is really important if you're doing upgrades or patches, or you want to verify the capabilities of the machine as you're evolving your control strategy. So we'll take a look at like the operating system, and the version is 5.11.0-38 low latency. It just gives you an idea of how much information is here for you to be able to have total control over your control system. Okay, so we'll go back. I'm going to go ahead and hit Discover. And all right, so it's discovered all of these new devices, and it's now pulling all of that Redfish information into the information model. So we'll go back to our DCNs, and we'll start waiting, and you can see it's starting to add some VCAL devices. So this might just take just a minute or so. So we got 4 of the 11. Okay, so I'm just going to hit refresh one more time, and there we go. You can now see if I filter to VCAL, we have all 4 of the VCAL devices there. We can take a look at ASRock, and you can see all 5 of the ASRock devices are there, as well as the Phoenix Contact. Just clear those. I want to point out that we did not need to shut down the control system to add these new components. In many cases, this is true not only for adding new hardware, but for installing new software, installing patches, and performing other system lifecycle maintenance activities. So to summarize thus far, we've shown that our open process automation based QuickStart system is 1, a functional control system. 2, it allows business value creation by easily inserting new technology. And 3, it reduces the initial and total lifecycle costs through modular interoperability. But we're not quite done for this demonstration. Tom is going to walk you through something new. Tom?
Okay, I have just one more thing that we want to show you today. This is going to be a model predictive control solution to the same control problem that we saw earlier with the fired heater. So let me bring back our ignition HMI. And down here I have another Python GUI that we're going to use. All right, so why did we want to do this demo? Well, we're trying to demonstrate compute power, scalability, all of that's available in this new OPA architecture. Using it and exploiting it, we can get a much more effective control solution for this problem. Model predictive control. Let me say a few words about that. So that's been a major thread in my technical career over the years. The difference is that instead of individual controllers that are trying to cooperate, you develop a single mathematical model of a whole system, in this case, this whole fired heater. And you hand that over to the control algorithm, and that gives the control algorithm a holistic view of the entire unit. Using this model then, it can see the effects of everything on everything else, and it can predict out into the future, so it can anticipate things that'll happen, like hitting constraints in the future. So this technology has been very successful, particularly in chemical plants and refineries around the world. Now, you may know it by a different name. There are brand names, Dynamic Matrix Control, DMC, from Aspen Tech. There's a Platform for Advanced Control and Estimation from Yokogawa. But down under the hood, it's this same basic idea of model predictive control. Now, using DMC and PACE with current DCS systems is quite frustrating. And it's frustrating because those architectures limit what you can do with model predictive control. The problem is that you have to run this technology way up at the top in a separate computer, and the DCS actually blocks your path down to the I/O. And so as you're doing communication between the MPC and the I/O, you're using outdated communication protocols. The bandwidth isn't what you need. And the result is that you can't run as fast as you would like to, and you can't have the large scope of problem that you would like to. All right, so that's very frustrating. In the best of all worlds, you'd like to run DMC and PACE at the edge, where you have that close communication with the I/O. And you'd also like to, if you can, take the latest, greatest MPC technology from the academic world, or even AI technology, and also run it at the edge. And that is exactly what open process automation allows you to do. Okay? So that's what I've done here. I've implemented a state-of-the-art MPC solution for this problem. This is taken from some academic work that's very recent. So it's implemented in Python, and we're using a couple of packages from academics. We're using MPC tools from my longtime collaborator, Jim Rawlings at UC Santa Barbara. That in turn uses an optimization code called IPOpt from Larry Biegler at Carnegie Mellon. And we're also using a technology called Custody to get exact derivative information for the optimizer. And that comes from Professor Diehl's group at University of Freiburg. So it's a state-of-the-art solution. It also runs very fast. It runs every 2 seconds. And it's running on one of the ASRock DCNs, one of the i7 DCNs. As it's running every 2 seconds, it's solving 3 optimization problems. The first one is a moving horizon estimator that tells the control what's going to happen in the future if nothing else has changed. Then there's a second one that figures out the best steady state for the heater to operate. Then there's a third one that is a dynamic optimization that figures out the best adjustments to make to get the heater from where it would go to where you want it to go in the future. And all that happens every 2 seconds. Okay. Now, as part of that, we can program some priorities into the control. And so what we've told it is that the top priority is those tube skin temperatures that we talked about earlier. We don't want to violate those limits. And we've told it that we would like to maintain a set point on the outlet temperature. And we said that is more important than the total flow rate constraint. So if we have room, we want the total flow rate as well. Okay, so recall earlier I showed you a conventional control solution using PID blocks and selector blocks. We increased the set point on the outlet temperature of the control of the heater. It introduced more fuel gas and temperature rose. The temperature of the outlet was coming up to getting close to where we wanted it, but it didn't quite get there because these override controllers, which were looking after the tube skin temperature limits, prevented the fuel gas from going any higher. And with a conventional strategy, it's going to leave the system parked there. It'll tell the operators that, this is where it's at, but it's not going to do anything else. And that's a little unsatisfying because, you know what an operator would do to get around that situation. And what we're going to show you is that model predictive control can resolve that in a much more effective way. And that's what we're going to do right now. We'll do the same experiment. So the model predictive control is running, and I'm going to change the outlet temperature set point up to 790. Very carefully. And so what we're seeing here is the red line is current time. And so here's my set point change. And the controller is predicting this is what's going to happen in the future to the outlet temperature. It also says that the tube skin temperature is going to briefly go above this limit and come back down, but it's not going to go so high that it alarms. Before we saw the alarm go off, right? So before the alarm happens, the controller brings the tube skin temperature back down, and now it's going to ride this limit for a little while in the future. And it also says that it's going to bring the outlet temperature up to its set point. And the way it's going to do that is to back feed out of the heater. So we're going to give up on our feed set point so that we can achieve our outlet temperature set point. And that's the priority that we programmed into the controller. And so this is the real value of model predictive control. You can set up priorities. You can respect constraints in a much more effective way. And with other types of applications, pretty much any MPC that I've implemented in a refinery, you can increase the throughput to the refinery by a tiny amount, say 0.5%, and you'll make multiple millions of dollars a year. So this is very effective control technology, and it's great to have finally have a kind of system where we can experiment with new technology in this way and implement MPC at the edge. That concludes the demo portion of our showcase. Now I'd like to turn it over to Bob Hagenow, the CEO of Seaplane.ai.